try to solve every problem with a graph, we'll be at it all night, and we'll be out of graph paper before next week. Let's translate what we've learned into algebra. We already have one equation of motion, the definition of acceleration. Acceleration equals the change in velocity over the change in time. There it is, our first one of 5. Put a box around it and take it away. Now, let's hit it up with some algebra. Change in velocity is final minus initial over change in time. Let's start the stopwatch at 0 seconds so we don't have to deal with a change. Now, multiply both sides by the time, cancel, and you get AT equals final velocity minus initial velocity. We want to find final velocity, so add initial velocity to both sides. What do you get? If you want to know your instantaneous velocity without having to read it off the graph, your final velocity, check on that direction, is equal to your initial velocity plus your acceleration times time. Second law of motion, put a box around it. That'll tell us how fast we're going there. Now for displacement. Displacement's going to be a little bit more complicated. We found on a graph that you could either measure your displacement directly, or you could find the area under a velocity time graph. Well, here's a velocity time graph. We start at an initial velocity, we go to a final velocity at a constant acceleration. That's important. If the acceleration isn't constant, we won't be able to use this clever method. In any case, here's our shape that we have to find the area of. Yuck. I don't have any geometry class formulas for this. What I do have is a formula for the area of this rectangle down here. That's base times height. I can do that. And a formula for the area of this triangle up here. That's 1/2 base times height. I can do that too. Well, let's get started. The base for the same is both. It goes from 0 to t. I believe that is t seconds long. The height of this one is our initial velocity. So our change in displacement will be our rectangle, base times height, plus our triangle, 1/2 base. Well, we know our base is t, and our height. What's the height of the triangle? The height of the triangle up here is VF minus VI. VF minus VI. Wait a minute. VF minus VI, I've seen that before. That's equal to acceleration times time. Acceleration times time, that simplifies. Our change in displacement is equal to initial velocity times time plus 1/2 of our acceleration times time squared. So there is our equation for change in displacement. Change in the displacement equals initial velocity times time plus 1/2 acceleration times time squared. Congratulations, you found it. Write it down. Put a box around it. Also note that if we wanted the area under the graph, we could have also taken this big rectangle here, final velocity times time, and subtracted not this triangle here, but this one there, which is also 1/2 AT squared. We got 2 formulas for the price of 1. If you know the initial velocity, use this version. Add the small rectangle and the large triangle. If you know the final velocity but don't know what was happening at the beginning of the problem, use this version. Final velocity times time, the big rectangle, minus the other big triangle. Write it down, put a box around it. All 4 of these equations assume we know when things happen. They all depend on time. What if you didn't have a stopwatch? Well, above, we found out that final velocity, initial velocity, and time were all closely related. They were related by acceleration. Solve for t. Pause, then press play to check your work. There, divide by a. Now substitute this time every time an equation tells you need time. Do the substitution in your notebook and press play to check your work. Oh, yuck. Do we really have to do all that distribution? Yep, afraid so. You gotta do VI times VF minus VI times VI. And, oh my gosh, we're gonna have to FOIL this out. VF minus VI times VF minus VI. Hold your nose. do your distribution, pause, and press play to check your work. So that's going to give you VIVF over A minus VI squared over A plus A over 2 times all this mess. Wait a minute. That cancels out. This A is going to cancel out with one of these A's. And this 2 can come over here to join. Cancel out your A's, distribute to your 2, and see if anything matches up. Hold on, check this out. You've got 2 VIVF over 2, and that cancels out. And wait a minute, over here, look, we've got a VIVF over A on the left. We've got a VIVF over here on the left to cancel this one out on the right. Goodbye. They're gone. Cancel them out. A positive VI squared over 2A here and a negative VI squared over 2I there. Yeah, I know I had a negative sign there 3 seconds ago, but it has taken me 4 honking hours to make this video that I could have done in 4 minutes on the board, and I am not starting over again. Yes, negative VI times negative VI. It's a positive number. Deal with it. Anyway, wait a minute. This is positive 1 of VI squared over 2A. This is negative. Do they cancel out? No. Positive 1/2 minus 1. Positive 1/2 minus 1 is negative 1/2. We can simplify like this. There, like terms. Positive 1, negative 2. We'll be left with negative VI squared over 2A, half of what we had before, and negative. I'm getting really tired of those 2A's. Can we multiply this whole side by 2A and this whole side by 2A and get rid of those fractions? Because if we can, it's all going to look like this. Our fifth equation of motion, the one that does not depend on time. The one that does depend on how fast you're going at the end, how fast you're going in the beginning, your acceleration, and where you ended up. Please note that taking the square root of this equation is not as easy as it seems. If you want this to say VF equals, you cannot split this square root across the plus sign. The square root of 2 plus the square root of 2 does not equal the square root of 4. It is nasty. This side must stay. And if you take the square root, you have to make sure that you have both the positive answer and the negative answer. Is the problem going forwards or backwards, up or down? You decide. In any case, you'll know how fast it's going when it's there. Now, you've got 5 equations of motion, and they will tell you where, when, and how fast. You are good to go.